way up there. Now, before we begin, I want to talk a little bit about bonds, chemical bonds. There are three main chemical bonds. They are covalent, ionic, and what's the last one? Anybody? Covalent, ionic, one more. You got, yeah. These are the three main bonds between atoms. Let's look at the covalent bond for a moment. Consider plastics or rubber or other things. Look at, so I've got one here for polyethylene. A plastic. And this is a carbon chain, organic chemistry. We have carbon chains. And going to one side is hydrogen, 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 hydrogen. This is the base. And for however number of bases you need here to make it a complete chain. If we look at the electrons on this, the valence electron is what I'm interested in. Carbon has 4 valence electrons. 1, 2, 3, 4. These are ready to make bonds. Same with this carbon, 4 valence electrons. Hydrogen has 1 valence electron. Hydrogen has 1 here, 1 here. So the hydrogen will bond in order to have 2 and use up those electrons. These will come together. And this carbon here will come together with that one. These two will join. And this carbon has 1. Those two will join. These will all join. As a result, all the valence electrons are being tied up. They are all used. All valence electrons are used. Thank you. And none are available to do additional work. This is your basic chemistry. Let's look at ionic bond, common ionic bond, sodium chloride. Sodium chloride. The valence electron for sodium is just 1 electron. Chlorine has 7 valence electrons. It is highly electronegative. Being highly electronegative, what it will do is it'll pull that electron over to here such that it makes an octet. Just like these ones here are all octets if you add them up. Makes an octet, and leaving sodium short 1 electron. As a result, sodium gets a plus charge. If this has an additional electrons are negatively charged, they will have a negative charge. So these two will combine electrostatically. This is an ionic bond. Again, all the electrons, all the valence electrons in here are being used in order to make that bond. None are available to do work. And there's one left over, and that's the metallic bond. Consider iron, copper, iron, it doesn't matter. Since we're working with electricity, copper is common. So I'll just use copper. Here are copper ions, or copper atoms. I don't exactly know how many electrons are in the valence electron, or valence orbitals of copper, but copper electrons have valence electrons like this. See, there's 2, copper 2 plus 2. Now these electrons, they are shared. Electrons are shared among all of the copper atoms, every one of them. So this electron will travel to here, that electron could travel to there, could travel to here, that one will travel there, this one will travel here. They all travel about, forming what's known as an electron cloud. You have an electron cloud. These electrons, since they are free, they are available to do work, electrical work. They can conduct electricity. Now electricity is the movement, electricity is the movement of electrons. Movement of electrons. Let's do a demonstration to prove this. I have here a multimeter. As soon as I get it, I got a lot of paraphernalia here. Put this multimeter together. I could have bought a digital one. I like the analog one here with the needle that deflects. I just have to give that some wires. So one's black, one's red, one's negative, one's positive. I just have to put them in here in the proper places. Let's see, the negative will go, that's ground, positive goes here. I'm going to turn this to resistance. Resistance has the unit of an ohm. You can see ohms right in here, so I got it in resistance. This is one way to determine if a piece of wire is broken. So right now there's a battery inside. The battery is sending electricity around these wires. In order for me to measure resistance, I have to make a connection. So these are the two electrodes, the black and the white. When I make the connection, it'll show a movement. In there'll be a deflection here with the needle, as you can see. So it tells me I have a complete circuit. I'm not checking voltage, I'm checking resistance to see if if the wire was broken here, I wouldn't get anything else, like so. But when I touch it, I get a deflection. So I know it's conducting electricity, or can conduct electricity. So let's do a couple of items. I said plastic doesn't conduct electricity. Okay, let's see if I can get a piece of plastic or something similar to it. This is Bakelite. It's a hard plastic is what it is. And if I were to touch the electrodes on both sides of the Bakelite, there is no deflection in the needle. That's because this is a covalent bond. So let's do something else. Here's an elastic band. Again, same thing. Let's find out. If I touch it, there's no deflection. Again, covalent bonds. So covalent bonds don't conduct electricity. What else do I have here? I don't have salt for ionic bonds, so I'm not going to do that. But here's a chunk. It looks. What does this look like? Gold. It looks like gold. It's also called fool's gold, also known as pyrite. Pyrite is a combination of iron. Is iron sulfide. There's iron in here plus sulfur. Because it has iron, and iron is a metallic bond as such, one would expect that this will conduct electricity. Let's find out. And it does. There it is. So iron pyrite, or pyrite, iron sulfide, because there's iron in here, it will conduct electricity because of the bonding structure that it has right here. It has this cloud of electrons. I have with me, well, here's my wedding band. It's gold. I were to put connection here and the connection on top. Obviously, gold does conduct electricity. All metals will conduct electricity, as will copper. That's the reason we use copper wires in homes. Let's find something else in here. What do we have in here? Oh, here's a nice gem. It's some sort of a stone. Let's see. Will that conduct? Nope. Covalent bonds. No conduction. Moving on here, let's have a look at paint. Paint is a plastic. When you paint the wall, you're basically putting a plastic on that wall. And let's see if paint will conduct electricity. And the answer is no. What about wood? Well, wood, we're back in the world of organic chemistry, which we just did. So here's open wood right there and here. And between the two, be stubborn here. Here we go. The answer is wood does not conduct electricity. They're good insulators. What about graphite?
Yes.
Will graphite or carbon, that's what this is, we call it pencil lead. I don't know where the word lead comes from, nothing lead here, it's all carbon. Will it conduct?
Yes.
Yeah, that got a yes, let's find out. The answer is yes. So how come this carbon conducts electricity and yet that carbon doesn't? That's because in graphite, the 4 free electrons, 2 of them are used to make the bond, very loose bond. The other 2 are still free to move around. As a result, this is known as a semiconductor, as well as silicon. They're both semiconductors, and that's the reason we have the electronics today. So carbon does conduct electricity, or graphite I should say, and it follows these basic rules right here. If all the electrons are being tied up, it's going to be an insulator, same as this one. And if it has a cloud of electrons, the electrons are free to move, we have electrical conductivity. Now I say that with some reservation, because if I put enough electricity on this wood right here, get enough current through it, it will break those bonds and start to generate electricity and burn the wood. But for everyday purposes, we plug into 120 volts, 15 amps in our regular homes, this applies. Here we are on the home page. We are in week 11, and this week's topic is electricity. As you can see here, assignment 7 is due next week on Monday, November 20th. But let's have a look at week 11. We'll go to modules. Scrolling down to week 11. Let's see what we have. Week 8. Here's 11. There's lots of information here. Let's see if I can explain some of this for you. Key topic sheet. You see the ones that I write. Let's see what's important here. And I discuss covalent bonds, metallic bonds, and ionic bonds. Here they are. Just like the examples that I just showed you earlier. Down at the bottom of all of this, there's a lot of information here regarding voltages and currents and resistance, but here is Ohm's law, V equals IR. And further down is an understanding of the units that are used. For voltage, well, voltage is represented by the letter V, capital V. Should be here that this is just electricians doing their thing, E representing electromotive force or energy. But for our purposes, the voltage is V, voltage, and it has a unit of a volt. Current is represented by the letter I, and it has a unit of an ampere. And resistance has the letter R, capital letter R, and it has a unit of an ohm. And ohm is represented by the Greek letter omega. For the assignment, just write down the word ohm. When you have a resistance like 10 ohms, just write down 10 and then the word ohm. You could use omega, but I find that Excel has a tendency to change omega into a W, so it looks like this. So you could be telling me 10 ohms, but I will see 10 W's, which represents watts, which brings me to power. And power is capital letter P, and it has the unit of a watt. And work and energy, all energy, as I've said earlier, has a unit of a joule. This was in past classes. Up above is Ohm's law. V equals IR. It says voltage is equal to the current times the resistance in the proper units. Now they have to be, when you use that equation, it has to be the full volt, not a millivolt or megavolt, just regular volts. It has to be amperes, not milliamperes, mega amperes, microamperes. It has to be amps. So you have to do the conversions to proper full amps, proper full volts, and same with ohms. Otherwise, using this equation here will give you a number, but that number will be, well, meaningless, because they all have to be in full value of volts, full value of ohms, or current is
amperes, and resistance, ohms. And this is Ohm's law. Let's go back and see what else I have posted. So this is a PowerPoint, electricity and electric circuits. You can view this at your leisure. There's a lot of information in here. I'll leave that for you. And there is another PowerPoint for FIS 10008. Again, I will leave this for you to review. Lots and lots of information in here as well. Go back some more. What I'm really interested in discussing right now is this one, conventional current. Now, as you saw from my demonstration, electricity is the flow of electrons. Let me just download this. So when you turn on the switch, light switch in your home, the electrons are flowing, going into the light bulb and generating some heat and giving us light. Let me just open this up here. That is based on what we know today about atoms and electrons and electricity overall. But long ago in 1800, 1810, 1820, 1830, they didn't know about electrons. They didn't know about atoms, for that matter. And let's see what I have here. And there were some individuals who were working with the electricity at the time. They called it a charge. It was a pile that they were actually working on. Volta come up with this alternating layers of copper, zinc, and some electrolyte in between. And this combination of metals he called a pile. Today we call that a battery. So back in the day, the 1800s, 1820, 1830, there was Benjamin Franklin, Michael Faraday, Alessandro Volta, and others working with this pile, trying to understand electricity. And it says here, therefore, all the laws and rules for electric circuits were based on a direction from the positive terminal of the source of EMF through the external circuit and back to the negative terminal of the EMF. This was based on Faraday's observations. Around 1830, Faraday noticed when he was doing his experiments that there was a charge traveling through the wires, and he had to give it a positive or a negative. So which way is this charge going? Based on his observations, he chose that a charge was leaving the positive side of the battery, which at that time they called a pile, but it was leaving the positive side of the battery and going into the negative side. This is now called convention. So when a charge leaves the positive terminal and goes around the circuit and back into the negative terminal, this is now called convention. In reality, electrons flow from the negative side of a battery and into the positive side of a battery. Going further here, there's more information on this. This information can be very, very confusing. But down at the bottom here, this flow of charge from the positive side to the negative of a battery is known as conventional direction for electric current, or simply conventional current. Allow me a moment to simplify this in today's words. I'm going to go back to modules, and let's have a look at some of my examples that I have posted for electric problems. This one. And I won't download these. I think they're pretty visible. These two lines represent a battery. The short one is the negative terminal of a battery, and the long one is the positive terminal of a battery. By convention, based on what Faraday said back in 1830, a charge leaves the battery from the positive side, goes around through the circuit and back into the negative side. At that time, he knew nothing about electrons and atoms. That stuff came around 1900, 1905, 1910, 1920. So some 50, 60 years later, we learned about electrons. So today, based on what we know about electrons and how electricity moves through wire, it is the electrons that is actually carrying the current. This is known as electron flow. And in reality, electrons leave the negative side of a terminal and they go around into the positive side. This is what's known as electron flow. However, electricians are staying with conventional flow. When they draw a diagram like this one, they like to stay convention. Mathematically, so the argument goes, mathematically it doesn't matter. For our simple case, this is true. Mathematically, if I were to calculate the resistance here, what I'm looking for. What is the resistance? If I use convention, the flow is this way. It really doesn't change the equation any. It's still V equals IR, and the answer is 60 ohms. If I were to use electron flow, the equation is still Ohm's law, V equals IR, and the electrons are flowing around the other way, but it has no impact mathematically, and the answer is still 60 ohms. As a consequence of all of this, today's electricians still work with convention, which means that a charge is leaving the positive side of the battery around to the negative. Sometimes when they have to, in the world of electronics, they will go electron flow, which is electrons will leave the negative side of a battery and travel towards the positive side, which is what they actually do. But we're going to stay with convention, just like all the other electricians. And you'll notice here in all my examples, the current, represented by this arrow, and I represents current. Current leaves the positive side and goes around in this direction, following convention. And the same with this diagram. Current leaves the positive, going around, following convention. And same with this one. And this one. Do I have any more? Nope. Now I'll just stop here. Let's go back and have a look at our equations. Our equations, oh, they're way up at the top somewhere. We go way up here, find our equations. Here is the formula sheet. Oh, there we go, formula sheet. And these are the equations we'll be using for electricity. I gave a long little blurb here regarding why there are so many equations. And physics is nothing more than the study of nature, and math is the language of nature. That's how nature speaks to us, and we in turn understand nature via mathematics. So where are we here? Here it is. Here is Ohm's law, V equals IR. We're not interested in this one. This has to do with resistivity in a wire. Here are three power equations. Power is equal to current times volts, or power is equal to I squared, current squared times resistance, or power is equal to voltage squared divided by resistance. All three of these will give you the exact same answer. All depends on what you have available to use. If you have current and voltage, we'll use this one. If you have voltage and resistance, use this one. And the same applies here if you have current and resistance. But they will all give you the same answer in power, and power has the units of a watt. We're not really too interested in energy, although I do use it in one of my examples, but that's just to arrive at a dollar sign. And we are interested in these three. This Req represents resistance equivalent, or the equivalent resistance of a series circuit. And these three resistances are connected in series. And this is for resistances in parallel. So 1 over R equivalent, we're looking for the equivalent resistance of a group of resistances or resistors. In this case, when they are in parallel. Be careful of this equation because it's 1 divided by Req. So you have to do a little bit of algebra. And this one here is also for resistances in parallel, but it's only valid for 2 in parallel. Where here you could have 2, 3, 4, 5, 6 resistances in parallel. This one is only used for 2 resistances in parallel, and I've given examples of that.